For this week's discussion, I wanted to have people take a look at the ChemLibra text and to post a problem that they looked at and that they found a little bit more challenging. Also, I wanted to point out that we've updated a little bit of our ChemLibra text. The agenda finally has a couple more weeks. Week 4 is complete. Week 5 we're working on. So we do have chapter 3 that needs to be covered this week. Some of the pages in chapter 3 have practice problems, and there's also a week 4 practice sheet. So we have 5 different pages that have practice problems. Then we also have some videos that could be helpful, and these are content. So the discussion this week has to do with practicing some of these problems. And this time, I think it's a little bit better because the answers are provided. If you just click on it, it gives the answer. But I would strongly suggest that you should try to do these on your own and then check the answers to see if you are getting them right. If there's one that you didn't get right and you don't see right away why you didn't get it right, that would be a good one to post to the discussion. But at least even if I don't get to the discussion as soon as I would like, the answers are available to you. And I do want to apologize for my lateness in getting the discussion from the other week. I know a lot of people had issues with that, so I want to include a little explanation in case your group was not able to help you understand those problems. It really is important to understand them before we move on. So we have 2 machines that dispense 12.5 ounces, or are supposed to dispense 12.5 ounces of cereal into bags. And we have a more accurate machine that's less precise and a more precise machine that's less accurate. So what would make one set of measurements more accurate? Accuracy is how close you are to the target value. So if you had a group of accurate measurements, then when you average them, they're pretty much centered around the true value. Let's go ahead and draw a number line. So the true value is 12.5 ounces, and it looks like the machine A values, let's put some X's, they're centered around that true value. So when you average them, they're pretty close to the true value. But they're not that close to each other. They're kind of spread out. So the machine is not very precise, but it's accurate because it's centered around that value that we're aiming for. Machine B is more precise, so the grouping is much smaller. That's what makes it more precise. The values are very close to each other. But the average is a little bit far off from where we were aiming for. So it looks like for this machine, machine B maybe needs to be adjusted, but if it gets adjusted a little bit and we can move those values over here, we'll have a good precision and a good accuracy. Right now we only have a good precision, not so great accuracy. I think some students had a question of how to calculate the average. Whenever you want to average a group of numbers, you want to add them up. So the sum of all these numbers, if you add them up, we get 67.5 ounces in 5 bags of cereal. So we would divide that by 5, and we would get 13.5 ounces as the average. So we're going to add up, well, we'll say divide by the number of measurements. So if you were averaging 4 or 6 measurements, you wouldn't divide by 5. When we add these up, we get a sum of 63.0 ounces, and when we divide that by 5, we get an average of 12.6 ounces. So here we have the averages of the 2 group. That was the next question, calculating the average. The percent error is how far is it from the true value. So we have your value minus the true value, and then you can take the absolute value. So if your number is too small, you can not have the negative sign, just take the magnitude, not whether it's plus or minus, just take the distance. How far is your value from the true value? And then we express that as a percent by dividing it by the true value and then making it a percent, a 100%. Let's do this a little bit more steps. We'll show a little bit more steps. So the 0.1 ounces, we divide it by 12.5 ounces, and then we multiply by 100%. The ounces cancel. We get 0.008 times 100%, which gives us 0.8%. Put that there. So the average for A was 12.6. The percent error was 0.8%. Let's take a look at the B. We already know the average was 13.5 ounces. So we have the difference between the two values over the true value times 100%. So that's 1 ounce over 12.5 ounces times 100%. 0.08 times 100%, which actually comes out to be 8%. So that makes sense because the difference here is 0.1 ounce and this is 1 ounce. So it's 10 times bigger in ounces. It's also 10 times bigger in percent. All right, let's take a look at these significant digit problems because it's very important for people to understand this. We're going to be using this the whole class. So for this one, we have 3 significant digits. The 5, the 6, and the 7 are significant. These 2 digits are to the left of the non-zero digits, and so they are not significant. So we have 3 significant digits. Now we want to round it to 2. So we just want to keep this one and this one. This one we're going to get rid of. Since it's large, we're going to bump up the 6 and make it a 7. So we're going to round that to 0.057. 1, 2, 3, 4, and 5 significant digits. This 0 is to the right of the non-zero digits, and that depends on the decimal. Since there is a decimal in the number, it is significant. So that is 5 significant digits. We only want 2, so we want to keep just these 2. So we're going to keep the 3 and the 4. The 2 is small. We're not going to change the 4 to a 5. But to make this 340 something and not 34, we need a placeholder 0 and not a decimal. If you chop off digits that are to the left of the decimal, you need those placeholder zeros. Otherwise, you're changing the value of the number. So we don't want 34. When we round off a number, we don't want to change it by dividing it by 10 or 100 or something like that. So for this last one, we have 1, 2, 3, 4 significant digits. The 0 in between non-zero digits is always significant. We have the never, the always, and then the right we have depends on the decimal. This number does not have a decimal, so these 2 are not significant. We do have 4 significant digits. If we want to round it to 2 significant digits, we'll keep the 2. We'll change this to a 1 because the next one over the 6 is rather large. And now, again, we don't want to change this to just 21. This is 206,400, so it does not round to 21. Rounding means approximately what is this? 206,400 is not approximately 21. It's approximately 210,000. So we do need those placeholder zeros. So it's not 21 for sure. All right, let's see if we can provide the calculations with the correct significant digits. For subtraction and addition, it's good to line up the numbers just so we can tell where the uncertain digits are, because subtraction and addition are based on place value. All right, we have the numerical answer. Now let's figure out the uncertainty. This first value has uncertainty in the ones place. It's plus or minus 1. It could be 4,582. It could be 4,584. It's plus or minus 1. This has the uncertainty in the tenths place, 1 after the decimal. It could be 5.9. It could be 5.7. It's plus or minus 0.1. So our result has uncertainty in both the ones place and the tenths place. And this is not what we're supposed to have. We're supposed to have the last significant digit be our uncertain digit, like it is for this number and it is for this number. So we're going to need to round this to the ones place so that we can have uncertainty just here and not in two places. If we're not sure if it's plus or minus 1, who cares about this 0.2 over here? So we have to round this off and make it 4,577. And we're uncertain in the ones place. If we do division, then this one is based on the number of significant digits. So my calculator tells me this is 790.1724138. So we cannot be this certain about the answer since we weren't that certain about either of the numbers we started with. For multiplying or dividing, it's based on the number of digits. So we have a 4 significant digit number being divided by a 2 significant digit number. So that means we need to have 2 significant digits in our answer. We're going to keep this one, and we need to get rid of the rest. 790. Remember, we need that placeholder 0 because 790.1724138 is not approximately 79, it's approximately 790. For this one, let's go ahead and do the division first. So we have 1.46 divided by 0.33. When you have multiplication and division and addition and subtraction in the problem, it helps to take it step by step. So 146 divided by 0.33. My calculator tells me is 4.42424. Okay. So we have a 3 significant digit number divided by a 2 significant digit number. So we should have 2 significant digits in our answer. Sometimes it's a good idea to just kind of underline to remind yourself how many significant digits you have, and then rounding off at the very end. That's the best way to do it. So our next step is to take this answer and add it to 7.12. We have 7.12 plus the result of our last calculation, our division result. So if I kept all the numbers in my calculator, it would tell me this. 11.5442424, I think it keeps going. So what I'm adding here is a number that is known to the hundredths place, 2 past the decimal, and a number that should only have 2 significant digits, so it's uncertain in the tenths place, 1 past the decimal. Then the result of my addition has uncertainty in 2 places. Again, we can't have that. So we need to round it to the tenths place. If we're unsure of the tenths, there's no sense talking about the hundredths and the thousands and all these other digits afterwards. So we will go ahead and round this off to 11.5. Some people, when we have a lot of conversions, just like to look, okay, I have a 3, and a 2. I'm going to round this off to 2. But when we add this, we do add one that only has 2 significant digits, but because it's more than 10, we get another digit over here. So we actually end up with these being known to 1 past the decimal. So the uncertainty is 1 past the decimal, so we can have 11.5 as our answer. Let's go ahead and underline all our uncertain digits here. So we have a 2 significant digit answer, one that goes 1 past the decimal, ends up with 3 significant digits, and one that goes to the ones place, which ends up with 4 significant digits.